Hello friends, so welcome to another video. So in this video we are going to solve one question that was asked in GATE 1993. So the question is the built-in potential in a PN junction, and the options are: A is equal to the difference in the Fermi level of two sides expressed in volts, B increases with the increase in the doping level of the two sides, C increases with the increase in temperature, and D is equal to the average of the Fermi level of two sides. Okay, so to understand this question, first we need to understand about Fermi level, about the energy band of p-type or n-type material. So let me just draw the energy band and Fermi level for p-type material, right? So this is for the p-type material. So let me choose another color. So yeah, so you have something like this, like, and yeah, this one. And yep. Okay, so this is for the p type. Let me draw similar for the n type, then we will see what are those line is all about. So for the n type, okay, so for the n type I will choose the same color for better understanding. Okay, and this one. Okay, band diagram for the p-type material, and this is for the n-type material. So in this band diagram you can see this, the lower most, this line represent the valence band EV, right, and the uppermost, this line or this band is the conduction band. Similarly for the n-type, this is valence band and this is conduction band, right? So what we say is the uppermost of the valence band and the lowermost of the conduction band. So this is the energy level, and this green dotted line represent the Fermi intrinsic level. Similarly for n-type, this is the intrinsic Fermi level, and this line beneath the intrinsic Fermi level is known as the Fermi level for p-type material, and this is Fermi level for n-type material, right? And as we know that p-type material has acceptor impurity or n-type has a donor impurity, so when we add acceptor or a donor impurity, so there will be a band right above the valence band in terms of p-type material. This is called acceptor level, right? Similarly for p-type E small a. So similarly for n-type material, the donor energy level will come right below the conduction band, right? So this is the p-type material, and this is the n-type material, and these are the Fermi energy level along with the conduction and the valence band. So now that we know about the p-type materials separately and the n-type materials separately, so what we are going to do now is we are going to merge p-type material and n-type material to make a p-n junction, right? So what is the procedure to do that? So normally in band diagram, what we do is we try to align either EFP, which is the Fermi level for the p-type material, to EFN, which is the Fermi level of n-type material. So what we do is we try to align, we try to make the energy level in a similar say energy level, same energy level. So either so for that what we do is either we make this thing a little bit upward, right, to match this level, or we reduce these n-type overall this band diagram to this level to match the EFP, to match the EFP and EFN. So here I am going to show you that how we merge p-type and n-type material to make a p-n junction, and when we do so, how this band bending occur. Okay, so yeah, so this is n-type material, this n-type material, this is p-type material. So what am I going to do is I'm going to now shift this p-type material to n-type material, or I'm going to shift the energy level of p-type material, right, so that I align the Fermi level of p-type material to the Fermi level of n-type material. So yeah, so this is what is the p-type material, right. So what I'm going to do is I'm going to align the Fermi level of p-type material, which is EFP, to the Fermi level of n-type material, which is EFN. Or you can do other way, that is either you can just move the EFN to match the energy level of EFP. So here what I have done is I have trying to match the EFP to EFN. So now here you can see that this level is aligned, right, this one is aligned. So this is what we need to do in order to make a p-n junction, or in order to see the band bending of any p-n junction, right. So so now what we have to do is we have to connect all the bands accordingly. Okay, so from here what we do is we try to align this Fermi level of p-type material to Fermi level of n-type material. So you can see that this Fermi level of p-type material is very well aligned with the Fermi level of n-type material. So accordingly what we do is we align other bands, like a conduction band and a valence band. So here you can see that there will be a bending, right. Similarly for here there will be a bending, and for the intrinsic semiconductor, this is Fermi level intrinsic semiconductor, there will be a bending. So this kind of band bending occurs between p-type, right. So between this kind of bending occurs between the p-type, right, between the p-type and the n-type material when we make a p-n junction. So now after knowing how to make a p-n junction out of p-type and n-type material, now what happens is, so this difference, right, so this difference is equal to the difference of the Fermi level of these two p-type and n-type material, because this much of bending has occurred when we try to align this Fermi level, right. So this bending, this bending is denoted as E phi b, or phi, right, E phi b. So this E phi b is what, this is the difference of Fermi level of EFN minus EFP, right. So the difference of Fermi level is equal to E phi b, and this E phi b is termed as built-in potential, right. So this difference is termed as built-in potential. So what we can see this, the built-in potential is equal, right, it is equal to the difference in the Fermi level of two sides, right. Fermi level of two sides, this one side n and one side is p. So the difference of the Fermi level of two sides is equal in built-in potential. This is called a built-in potential, right. So this is what is given in statement number 1, which is A. Okay, so now so far what we have understood is the p-type and n-type extrinsic semiconductor, right. We also saw that how when we make a p-n junction, or when we merge a p-type extrinsic semiconductor and n-type extrinsic semiconductor and make a p-n junction, how band bending occurs, right. and how built-in potential is formed, which is difference in the Fermi energy in both side, right? So okay, so here same energy diagram is shown for the p type. So let me consider for this is for the p type, right? Why? Because sorry, this is for the n type, this is for the n type. Why? Because the Fermi level is above the intrinsic Fermi level. This red dot is the intrinsic Fermi level, EFI. This is what? This is valence band, this is conduction band. Similarly here, this is EFI, this is conduction band, and this is valence band. So when the Fermi level is above the intrinsic Fermi level, which is here in case of n type, right? So it is called n-type material. In n-type material, the Fermi level of n-type material is above the intrinsic Fermi level. Similarly, for the p-type material, this is for the p-type material. For the p-type material, the Fermi level of p-type material is always below the Fermi intrinsic level of the material, right? Is always beneath the intrinsic Fermi level. So this is for the n-type material and this is for the p-type material. So now what happens when we dope, right? When we doped semiconductor with more, say, n-type and p-type dopant, right? When we do, say, acceptor or a donor doping, what happens to this EFN and EFP? So it has observed that when we increase the doping, right, when we increase the doping, then what happens is the Fermi level move away from the intrinsic Fermi level, right? So in case of EFN, this moves away, this moves upward, or I would say towards the conduction band. Similarly, when we increase the acceptor doping, what happens is this Fermi level EFE move towards the valence band, right? Move. So in this case, when we increase the doping, what happens is the intrinsic what happens is the Fermi level move away from the intrinsic Fermi level. So this is one thing to remember. There is one more thing, which is what happened when we increase the temperature, right? When we increase the temperature, what happened to the Fermi energy level? So when we increase the temperature, what happened is the Fermi level, right, move towards the intrinsic Fermi level, not away from the Fermi level, but it moves towards the Fermi level. So at this situation, when we increase the temperature, so let me choose another color. So when we increase the this temperature, what happens is this EFN move towards the intrinsic Fermi level. Similarly, in case of this p-type material, when we increase the temperature, this intrinsic this Fermi level EFP move towards the intrinsic Fermi level. So in one case, what we can see is when we do the doping, when we dope n-type or the p-type material, the Fermi level move away from each other, right? So there is a huge difference or gap between the Fermi level of n-type and p-type material, right? Similarly, when we increase the temperature, the Fermi level move towards the intrinsic Fermi level, right? So there is a gap. This gap is what? This gap is reducing because they both are coming towards intrinsic intrinsic Fermi level. So they both are coming towards intrinsic Fermi level. So this gap is reducing. But in case of higher doping, what happens is this is going this side, this is going this side. So as a result, the gap between EFN and EFP, as they are moving away from each other, right? This difference would be high, right? This difference would be what? This difference would be high. So what we concluded from this thing is, when we increase the doping, the difference, so let me write it down. When we increase the doping, when we increase the doping, the difference, which is EFN minus EFP, also increases, right? So this EFN and EFP is nothing but what? Our built-in potential, right? This EFN minus EFP is nothing but built-in potential. So we can say that as we increase the doping, the gap between the intrinsic level increases, and as a result built-in potential also increases. So this statement is given in what? Number B, right? Option B. So this thing is given in option number B. So the answer for this question would be A, is equal to the difference in the Fermi level of the two sides, as I have shown over here, right? This is equal to the difference of the two Fermi level, and answer would also be B. Why? Because it increases, right, with increase in the doping level of two sides. So as we increase the doping, so this thing, what would happen is, as we increase the doping, right, so here you can see that as we increase the doping for this one, so what happened is this will go down. So overall this gap will increase, hence this is what? This is potential, built-in potential or barrier potential is also increases. So the answer would be A and B.